All right. Good evening, everyone. I hope you can hear me now. My name is Jerry Kossoff, and I am here with Fiveable. And tonight, we're going to do some AP stats together. I hope everyone's staying safe. We're going to focus specifically on practicing some problems with t-tests. Of course, you can follow us at ThinkFiveable. That's where you can find lots of other content. And so tonight, what I wanted to do is spend a few minutes just reviewing, like, what is a hypothesis test, start to finish? What is the goal of it? What are we trying to do? And we'll do some multiple choice practice once we've reviewed that procedure. And then we'll specifically practice running some t-tests and do some free response scenarios with that. And so a t-test, you've got one sample t-test, you've got a two sample t-test, and you've got the special matched pairs t-test. And so we'll discuss the similarities and differences between those through a specific free response example. And at the end, do some more kind of big picture stuff. So before we hop into that quick review, just really big picture, the part of AP Stats that this is called inferential statistics. And the whole goal of inferential statistics is to gather information about a population using a sample. And the statistic you get from the sample will be the basis for the population parameter, the thing we don't know. I joke with my students, not very good joke, but this should really be called AP parameters, not AP statistics, because pretty much everything you're doing in the second half of the year is trying to figure something out about a population. So whether that's a population proportion or a difference of proportions, P and P hat, or a population mean or a difference in means, or you're working with mu and X bar. And the two big tools of inference that you are guaranteed to be asked about if and when we ever have an AP exam, that's a whole other story. But the two big things you're guaranteed to be asked to do are to build a confidence interval where you actually create a range of values for either the difference in things or a specific single population proportion or mean, or run a hypothesis test. And that's when you write a null hypothesis and an alternative, and then we run through a procedure to decide whether or not we're going to reject that particular claim about the null hypothesis. But at the end of the day, when you're running inference procedures, you're going to figure out what we want to talk about. What parameter are we trying to estimate or figure something out about? We're going to ensure that the conditions are met. We've got some conditions that we need to ensure are true so that all our math is right. And then we'll actually take our sample or two and do some calculations and make some kind of conclusion. In the case of hypothesis tests, there are four main steps that you need to do. And they are these guys. The first thing in the top left is to write hypotheses. Okay, and feel free to put in the chat things you already know about these. But hypotheses, we have an HO or a null hypothesis and an HA or an alternative hypothesis. The thing you need to know about these hypotheses is they are always about parameters. Yep, H null. And Brian, I'm going to take it a step further. Not just an equals, not usually an equals. The null hypothesis will always use an equal sign. And the alternative will always use an inequality of some type. Depending on if you want to say less than, greater than, or not equal, will depend on the context. But that null hypothesis, like thumbs down, null hypothesis will always use an equal sign. All good. And the other thing with these is they're always about parameters. So a way that exam writers will try to trick you is, especially in multiple choice, they'll sometimes put P hat and X bar in the hypotheses. That's no good. The hypotheses should always be about the population. So maybe the claim is 80% of people take the bus to school, or the average amount of time it takes to complete a certain task is 20 minutes. Whatever the claim is, that's going to be what the hypothesis equals. Or if you have two populations that you're trying to compare, you'll do mu1 equals mu2 or p1 equals p2. And it's always an equal sign in that. Once you've written the hypotheses, state, plan, do, conclude. Yeah, so if you're using the, I have one of those textbooks back here somewhere. If you're using the practice of statistics, the one with the flamingos on the front, at least that's the one we have, that four-step process of state, plan, do, conclude is exactly this. The reason I'm writing it out this way is when you look at AP rubrics, this is where the four sections usually come from. Sometimes they'll bundle some stuff together, but ultimately you're getting points for writing a hypothesis in the correct format. You're getting points for checking the conditions, which are that the sample or treatments are randomly selected or randomly assigned, and that the samples you're taking are big enough to ensure a normal sampling distribution. And then we actually calculate p hat or x bar. Then you take that p hat or x bar, get a test statistic, either a z or a t for proportions or means, which is going to answer for us how far away from the null hypothesis is this sample result. And the basic idea is if the sample result you get is really far away from what we believe to be the truth based on the null hypothesis, then either we got super unlucky with our sample and it's an outlier, or the null hypothesis is wrong and we can compare that test statistic and turn it into a p-value. And I see the hypothesis is always based on p. If you are running a z-test, yes, the null hypothesis will always be based on p, not p hat. And if you're running a t-test, it'll be mu instead of x bar. Always, always about the parameters. And then once you get a test statistic, we'll turn that into a p-value. Our calculator is going to do the test statistic and p-values for us 95% of the time. So at the end, we can talk about how to do it by hand. But for the most part, once you know what you're looking for, punch that in your calculator. It will give you a nice drawing for us. And if a p-value is very low, we will reject HO, which means we will have evidence for the null hypothesis. Basically saying, if the p-value is super low, that sample statistic we got is really far away from the null hypothesis, making the null hypothesis really unlikely to be true. Brian, in this stream, I'm not going to focus on type 1 and type 2 errors, but we can discuss them in context as they come up. Because you can always discuss, like, what would a type 1 error look like here? What would a type 2 error look like here? But I'm going to really focus on just the actual process of the hypothesis test. If you fail to reject the null hypothesis, if your p-value is not low enough, and remember that 0.05 is usually the typical threshold, that means we do not have enough evidence for the alternative hypothesis. And again, at the very end of this, when you're writing your sentences, notice we never say anything about accepting. We're not accepting the null hypothesis. Is the conclusion required to be written in a specific format? The requirements are always that you compare the p-value to the alpha level. So let's say our p-value is 0.02, and that is lower than 0.05. So I would say, since 0.02 is less than 0.05, I reject the null hypothesis. Therefore, I have evidence that whatever the alternative hypothesis was. And so who asked that? I think it was Mahitha asked that. We will see an example of that in a little bit. But generally, you have to compare your p-value to 0.05 or whatever the significance level is. You have to state if you've rejected the null hypothesis or not, and then explain what that tells you about the alternative hypothesis. Do you have evidence or do you not have evidence? Rejecting the null hypothesis gives you evidence to go with the alternative, and not rejecting the null hypothesis means you do not yet have evidence to go with the alternative. Vera is asking about pooled tests. Pooled is more of a thing for t-tests than it is for z-tests. And to be honest, it's not the kind of thing that the AP stats exam gets really like technical about. So we always can default to just no. Z-test versus t-test, absolutely. The very short 30-second answer is, if you're doing a test for proportions, it's a z-test. If you're doing a test for means, you're doing a t-test, at least in terms of AP statistics. We can run a z-test for means, but that's only if I know what the population standard deviation is. And if you're doing an actual statistical scenario of inference where you don't know stuff about the population, that's the whole point of the test. You won't know what the standard deviation is. So you'll use the sample standard deviation, which would require a t-test. But if you're working with proportions, there is no standard deviation because it's just proportions. So you'll do a z-test for that. So with that, this is like the big grand picture. Hopefully you guys have seen this before. I think we've done this in AP Bio. If you're in AP Bio, you have done chi-squared tests, which is like a topic we'll do in the future weeks. But yes, this general format of writing out hypotheses and then making some kind of calculation and getting a p-value is absolutely done in the AP Bio curriculum. So Allison, this should look familiar. Keywords to decide whether or not to use, 100%. If you see the scenario is about proportions, it's a z-test. If you see it's about averages, it's a t-test. And so that's really like reading the scenario will be a big thing. Rate as proportions. Yeah, ratios, that kind of thing. So let's get into some scenarios. Here is a scenario. We're going to use this scenario for several questions coming up here. So I'll give people a chance to read it. I'll read it out loud. In 2018, the students enrolled in honors classes in a large high school district spent an average of 13 hours per week on homework. Concerned about that number, the district implemented a new policy for 2019 aimed at reducing the amount of time students had to work at home by encouraging teachers to increase the amount of time during their classes dedicated to students completing independent work. In 2019, a random sample of 400 honors students was selected. The mean amount of time spent on homework per week in the sample was 12.5 hours, with a standard deviation of 6.5 hours. So before they ask us to do anything, some keywords I noticed in here, they're talking about average. They talked about mean. They mentioned in the sample, 12.5 hours was the mean and 6.5 was the standard deviation. So if I'm writing on my paper, I'm annotating next to that X bar is 12.5 and S is 6.5. And that's the sample data they gave me. There's actually only one sample here. There's not two samples. What I know is in 2018, the average was 13. So that's not from a sample. That's just like a fact from that year. So in that case, I would annotate next to that with a mu because that is the overall stuff for the population. So with that, which of these is an appropriate set of hypotheses for the district to test the claim that the average number of hours spent per week on homework was reduced as a result of the new policy? Mu is population mean, X bar is sample mean. Correct. Yep. Mu is the symbol if you're talking about a whole population. X bar is the symbol if you're talking about just a sample. And that's similar to how P and P hat interact. P is for a whole population. P hat is for just a sample. So some of you might be thinking about writing out some hypotheses. I'm going to give you some options here. Here are 5 options for you. Take a look at them and decide which one you think is the appropriate set of hypotheses for the district to test their claim. If you're not sure which it is, you can eliminate some and say, I know it's not this because of this, or I know it's this because of that. Okay, we've got a few going for A right now. Okay. All right, so I'm going to eliminate C because that's got a not equal sign in the alternative, but the specific policy was meant to reduce the amount of time. So we want the amount of time to be less than it used to be. All right, so I can eliminate C. It looks like a lot of people are saying A. Okay, oh no, I forgot to add my animations this week that would circle the answer. So I will just tell you without further ado that yes, you guys are correct. Shout out to you. It is A as in apples. D and E or B and E are no good because of X bars. That's the wrong symbol. And D seems like it could be legit because we're trying to reduce the amount from one year to the next. Although I just realized I put the wrong numbers on those. It should be 2019 first and 2018 second if I'm trying to reduce the amount. But there's not a sample of data. There's not a sample of data to deal with 2018. So reducing the amount is just compared to the number 13 is different than. Yeah, so Vera, if you look at answer choice C, what the scenario could have talked about would be the district wanted to change the amount of hours that students work. Like if they don't specify a direction, if they don't say increase, decrease, reduce, add, stuff like that, that implies a direction. If they just say change, different, things that don't imply one side of an inequality, then I'll just say not equal to. And that's going to change like some of the end calculations, but doesn't change how you end up running the test. All right, so we've got our hypotheses. Mu is 13 versus mu is less than 13. have the conditions for running a one sample t-test been met? So I didn't actually specify what they were, so I'm gonna try to draw out some knowledge from folks who've already covered this. Change the time rather than reduce the time. So here's some options for if the conditions for running a one sample t-test have been met. All right, so we're all had that dusty central limit theorem. So we're all in agreement that the conditions, like this is a yes, like we've covered what we need to cover, but it looks like we're not sure about why we've exactly covered it. So that 400, that sample size, definitely big enough to ensure an approximately normal sampling distribution. The standard deviation of the sample doesn't have anything to do with whether or not the sampling distribution, if I were to take many samples of 400 students, if I would end up with a nice normal distribution. I will, because 400 is a really big sample size. That should give me very consistent results. However, I need to ensure that the samples are random. The thing with this is if I want to run a one sample t-test, I don't need independent random samples. Independent random samples are for two sample t-tests, and there isn't two samples in this situation. They only took a sample in 2019 because the 2018 data was for the entire population. So if this was a situation where we took two samples of individuals in the different years and had the sample data from the two separate years, that's when I need to ensure that they were independently chosen random samples of students, with each being bigger than 30. But for a one sample t-test, I care about my single sample being bigger than 30. So the answer to this is actually going to be D as in dog, as opposed to C as in cat. Yes, we're good. The sample was randomly selected, and 400 is greater than 30. So random, check. Approximately normal sampling distribution, check, because the sample size is large enough. I saw a couple people use the 10% condition. Yep, the 10% condition is the sample you get less than 10% of the overall population size. You actually don't have to explicitly reference it on the AP Stats exam. It's never seen as a penalty though. Like it's never, like if you've been taught to do that, keep doing it. But it's not really going to come up as an explicitly tested thing. Which one do you draw a box plot for? If you've been given a graph of data for the sample, as opposed to just being told about it, and the sample size is really small, then that's when, to ensure that the population or the sampling distribution is normal, you have to sketch out a graph and look at the data to make sure it's not super duper skewed. If you have a big sample, it doesn't matter what the sample data looks like. If you have a small sample, then you have to make sure that the sample data is approximately normal to make it reasonable to assume that the original population was normal, to make it reasonable to do all the calculations that come next. So the whole point of these conditions is to ensure that the calculations you do will still be valid. If you don't take a random sample, your sample statistic is probably biased and isn't a good guess at what's going on in the population in the first place. And if your sample size is too small and you can't ensure an approximately normal sampling distribution, then all the calculations you do based on that normal distribution to get a z-score or a t-score aren't valid. And so the numbers won't really work out. Let me look at NPP. If you're referring to like n times p or n times p hat, that is in a normal probability plot. Gotcha. That can be a way to ensure that the original population appears to be normal. If the sample size is big enough, you don't have to look at it. If the sample size is 30 or more, the central limit theorem from a couple of units ago tells us that as you get bigger and bigger sample sizes, your sampling distribution becomes more and more and more normal. And no matter what the original population looked like, the sampling distribution will look approximately normal for any shape of an original population starting at about n equals 30. And that's kind of just like an accepted number of, once you get past 30, you're good. So if you got a really small sample, that's when you might need to look at a normal probability plot or making a literal graph of your sample. data. So if you've been provided NPPs before, that's cool. Don't always need them. All right, so we've written our hypotheses. Mu equals 13 versus alternative of mu less than 13. We've checked our conditions for a one sample t-test. Now let's see. At this significance level of 0.05, does the district have their convincing statistical evidence that the new policy worked as intended? On my TI-84, I'm going to go to number 2 and do a t-test. And I will give you a couple of minutes if you have a calculator with you to actually work it through. And then I will model on here working it through. So here, this is pretty much the standard multiple choice answers to hypothesis tests. Is they'll say 2 answers will be yes, 2 answers will be no, and the reasons will be based on the p-value. 2 of these answers are impossible. So if you know some facts about when you do or don't have evidence, then you can eliminate some of them, and then it's just a matter of getting the p-value otherwise. I'll wait about a minute to a minute and a half to let people punch some data in if they are running a t-test on their calculator, and then I will actually model on here what it looks like. All right, here's what I am seeing. All right, if I'm using a TI-84, okay, which I am, to do a statistical test, a hypothesis test, I use the button Stat, which is right next to the arrow key, and I slide over to where it says Tests. Gives me a whole menu of options. Numbers 1 and 2 are 1 sample tests for means. Numbers 3 and 4 are 2 sample tests for means. And 5 and 6 are z-test for proportions, 1 sample and 2 sample. I'm going to use number 2. This is a t-test. And then I scroll over to input statistics instead of data. Data is if they give you like a list of stuff, you can actually put it into your calculator. 99 times out of 100, you're going to be given the sample statistics, and so you want to put in stats. So then we know our symbols. I put in mu O, our null hypothesis, is 13. My x bar is 12.5. My S is 6.5. My N, sample size, is 400. And then the mean, my alternative hypothesis that I'm trying to test, is that the current mean is less than the null hypothesis of 13. Some people like to go to calculate then. I love going to draw after that. And I love going to draw because it'll actually create the distribution that I would be looking for and shade in the p-value. So this is going to be the sampling distribution based on the null hypothesis being 13. And then my p-value that I'm getting, so I got a t-test statistic of about -1.5. So what that's saying is if the null hypothesis is true, if the real answer is that it takes 13 hours still to do homework this year, then seeing a sample mean of 12.5 with a sample size of 400 is about 1.5 standard errors below the mean. That x bar is like kind of far away from where the mu is, but turning that into a p-value using the calculator, I get 0.06 for my p-value. So yeah, we do not have evidence because 0.06 is not less than 0.05. It is greater than 0.05. So my sentence, if I was doing a free response question, I would say since p equals 0.0624 is greater than 0.05, we do not, or we fail to reject the null hypothesis. I'll say fail to reject the null hypothesis, meaning we do not have evidence that the new policy reduced the mean. Where it's exactly the same. On an AP exam, the question will be made carefully so that you will definitely be either above or below. I believe what statisticians do is if you do exactly get 0.05, like quite literally 0.05, no good. It's got to be under the threshold. So 0.048, you're good. 0.05, not good anymore. Equation for finding a t-score. Yeah. So if you're going to do it by hand, Okay, the general test statistic is the statistic you get minus the parameter you have divided by what's called the standard error. So in this case, what I would do is I would put 12.5 for my statistic and 13 for the parameter. You always put the null hypothesis for that second part of it. Kind of like when you did z-scores way back in the day, you do an individual number minus the mean. Well, the mean of the whole population supposedly is 13. So I will go 12.5 minus 13. That's going to be my numerator. And then the denominator is the standard error. And you find that standard error, if you don't have them memorized, which you don't necessarily need to, the formula sheet for the AP Stats exam has a whole table of them. This is the updated one for this year, so hopefully your class is using them. And I can, at the end of this, I'll put a link to this, like a digital copy of this. And you find the standard error. The formula for standard error for a population mean is S over square root n. So you'll be given, in this case, S was 6.5 divided by the square root of 400. And so I know it's a mess on the screen right there, but if I put it in my calculator, 12.5 minus 13 all over 6.5 over the square root of 400, I should get about negative 1.5, which I do. And so this is how I typed it into my calculator screen, just like that. And that's what your calculator is doing behind the scenes. Unlike calculus, yeah. I teach calculus as well. My students are not always thrilled that they have to wait. We have to know all these facts and all these derivatives and all these antiderivatives and all these rules. Yeah, you do. AP Stats is a little nicer. So yes, you are given the formula sheets. Train data is the part I need help with. Yep. You will be given scenarios and sometimes just asked to run the test. Other times you'll be asked about the process of like, which is the right hypotheses, or, you know, have we met the conditions? But if you're doing it for your response question, it is a 100% guarantee that one of the first 5 free response questions will be a hypothesis test. End of story. Which type of hypothesis test remains to be seen, but you have to do the following 4 things. Write your hypotheses, check the conditions and name what test you're doing. And so that's the random condition, the normal condition, and then the test name. Some of you are going to ask about the 10% condition. 10% condition has never been explicitly scored on the free response rubrics. So you can check it and you can make statements about it. It is not going to count against you if you don't. The ones you need to check are that the sample's random or the treatments are randomly assigned and that the samples are big enough. Okay, you have to then get a test statistic and calculate a p-value. The good news is if you name what test you're doing, you can literally just write down the answer from your calculator. With a t-test, your calculator will also spit out the degrees of freedom. If you're doing a 2-sample, I thought the 10% condition is new course exam description. That is a really good, I had not heard that. So Veronica, I appreciate you bringing that up. And I will check on that and get back to you. So if you come in another week, I'll be able to do that. So sample size, degrees of freedom, if you're doing a 1-sample test, it's easy, 1 less than your sample size. If you're doing a 2-sample test, your calculator will actually tell you the degrees of freedom when you put the data in, because it kind of combines them in a way that honestly, I don't even know what the formula is for it. If you're running a 2-sample test on your calculator or a matched pairs test. When do we use degrees of freedom? Degrees of freedom are specifically for t-tests or t-intervals. So it's 1 less than your sample size, or when you're doing a 2-sample t-test, your calculator will tell you the degrees of freedom that it calculated for that situation. And it just depends on kind of the weights of the 2 samples. Yeah, I'll do my own extra research on this. I had not gotten any guidance from College Board that 10% condition was being included, but from my own study and own past readings, I know that it hasn't been a thing. So that's a good thing. And at the end, always interpret the p-value that you get. Mafuz, you asked about naming the test is a step in itself. It is, but it's not scored as as a separate component. Typically, if they're going to score these in 4 parts, these are the 4 parts that get scored. So the correct hypotheses using correct notation and equals and less than and all that good stuff is going to be the first thing that we score. The second thing that we score is that you've checked conditions and named what test you're doing. The third thing we're going to score is that you actually get your test statistic and p-value and they're listed correctly. And the fourth thing we score is that you then take that p-value and make a correct conclusion based on it. And if you get the wrong p-value, but you interpret it the correct way. So like, let's say you get 0.08 and you weren't supposed to get 0.08, but then you say, oh, we failed to reject the null hypothesis. I do not have evidence for the alternative. You're going to get the credit for the fourth part of it because you've correctly interpreted the p-value that you got. How do you get full points for the third thing? Here's the good news. Quite literally, write down t equals this, p-value equals that. If you've named, once you've named the test that you're doing, you just have to write down what the result is. You actually can lose points sometimes if you put incorrect notation somewhere, like when you're setting stuff up by hand. So it's best to name what you're doing and check the conditions and then just write down the results from the calculator because you're not going to lose anything for that, which is pretty cool. So let's do an example and we'll see some written out answers that get E versus P versus I. And then we can kind of do this together. So here's a scenario similar to one that we've seen in the past. A veterinary clinic is receiving complaints from dog owners that they have to wait longer than cat owners to have their pets seen. As pets enter the clinic, the time that they arrive until the time that they are seen by the vet, aka wait time, is recorded. A random sample of 150 cats and dogs is selected. Statistics regarding the wait time for each pet is summarized in the table below. So we've separated by cats and dogs. You have your sample sizes, you have your mean wait times listed, and your standard deviation of wait times for each type of pet. And then we're asked, at the level of alpha equals 0.05, do the data in the table provide convincing statistical evidence that the mean wait time for dogs is significantly longer than the mean wait time for cats? And the magic phrase, convincing statistical evidence. When you see that phrasing, that is your keyword to say, oh, I got to do a hypothesis test. Okay. Very rarely will the exam writers actually say, run a hypothesis test or conduct a test of significance. They will say, do we have convincing statistical evidence that whatever? And whatever comes after those 3 keywords is the alternative hypothesis, because that's what we're looking for evidence of. So if you don't know where to start, that's always a good place to start. Find the phrase convincing statistical evidence, look at what comes after it, or statistically significant. And whatever comes after that phrasing is your alternative hypothesis that we're looking to find evidence of. And then the null hypothesis can be written based on that. So the first thing we need to do is write hypotheses using appropriate notation or defining parameters. So I will let some people write some stuff in the chat box before I reveal what hypotheses I wrote for this. And we'll talk about what gets credit and what doesn't get credit. Would this be 2 proportions? All right. I think it's Mahitha just asked, is it 2 proportions? They don't say anything about percentages or proportions, but they do mention there are 2 groups. So I'm with you on it's 2, but they mention the mean. So this is a hypothesis test for means, not proportions. So you can write your hypotheses using the 2 groups. All right, so I see H null, the mu dog equals mu cat. HA, all right, Brandon. Oh, I love Brandon used the difference equaling 0. That is equivalent. If you're doing a difference of 2 groups, you can put the 2 groups on either side of the equal sign, or you can put them on the same side of the equal sign. Okay, and so I have similar ones to a lot of you guys. This notation will get E for essentially correct. Okay, this is kind of like the bare minimum that you could write to get the credit there. It uses a symbol for parameter, mu, that is widely known as population mean, and it uses notation of subscripts dog and cat that are given in the scenario. Okay, if someone had put like mu1 equals mu2 and mu1 greater than mu2, that would not get full credit because I don't know what group 1 and group 2 are. Okay, mu d and mu c should probably get credit because the D stands for dog and the C stands for cat. But it's best to write things out as much as possible. But what you don't have to do is write a whole separate sentence of like, mu dog refers to the mean wait time for the group of dogs in the sample, or the dogs in the population, because mu is a population parameter. I know some teachers will have people write out full descriptions of the parameter that they're looking for. But if you use conventional notation, you're good. So we've written our hypotheses. So based on the hypotheses you've written, you should have an idea of what test you're trying to run. Because I wrote mean, mu, I know it's going to be a t-test of some kind, not a z-test, because that's for proportions. So then we have to check our conditions and name the test. We always have to check randomness. We always have to check that our samples are big enough. And we have to name what test we're going to do. And your standard convention for naming the test would be something like, you do not need to state the alpha level when you state the hypothesis and define parameters. You do not in your written response yet because the alpha level was defined in the question. If the alpha level is not defined in the question, I think who asked that? Chovy asked that, then I would include the alpha level. The big idea is the alpha level has to be set before you start the test. And since they set it for us, we're good. We don't have to refer to it until we actually make our conclusion. If our alpha level is not set from the beginning, then we should assign an alpha level with our hypotheses. And to be clear, I'm going after this from a like what earns credit and what doesn't earn credit. Yeah, always assign 0.05 if not mentioned. Yeah, that's the standard significance level. That's the word I'm looking for there. So yes, if you really want to do 0.01 or 0.10, like that's fine. In the last 10 years of AP exams, the significance level has always been assigned for you in the free response section. Multiple choice sometimes won't put a significance level there because they're testing your knowledge of when you can and can't reject things, and the choices will have different alpha levels in them. But in terms of free response question, at least in my looking at the last 10 years of questions, the alpha level has been always set. So you don't have to worry about that. So let's check our conditions now. Okay. Is the randomness condition met? Yes, it is stated in the problem. Okay. Is the condition that we have a approximately normal sampling distribution, aka large counts, is that met? Why is 150 big enough? Okay. So it looks like Brian broke it down into 77 and 73. I'm going to get to that in a second. And then guys, write out what test would you do? What test would you run for this? So the standard, okay, 2 sample t-test. Okay, 2 sample t-test, 2 sample t-test. Is there ever, so someone just asked a really good question. Is there ever a free response question where conditions aren't met and we can't continue? When it's framed like this, do we have convincing statistical evidence that happens? I've never seen it. I have never seen the conditions be something that we fail. And we just have to stop. What I have seen is scenarios that have multiple parts to it, and like a part C is, could we run a 2 sample t-test for this? Why or why not? And then you discuss whether or not the conditions are met. So the only time I've seen conditions not be met is when we've been explicitly asked if they're met or not. But in the actual like running of the test on the problem that asks you to find convincing evidence of something, I've never seen the conditions be unmet. Okay. All right. So I've gotten some good answers in here. And this one, there's a little bit of a curveball here because you guys are all saying we want to do a 2-sample t-test. I agree. We're trying to compare the average wait time for cats versus the average wait time for dogs. That's 2 separate things to compare. But there was only a single sample. And that raises a bit of a red flag until we recognize, oh, wait, that one sample contained both types of pets in it. So even though there weren't 2 separate samples, we could consider the 2 separate groups of pets that come from the one sample to be 2 independent groups. And so even though they didn't come from 2 literally separate samples, they are independent groups of individuals, and the randomness condition is met. Typically, if you're doing a 2-sample t-test, you'll need to see something written about like literally 2 different groups. So we've assigned different, is that specification necessary? Probably, honestly, probably. That when you're doing 2-sample tests, they check for randomness and independence. And so it could be argued that because the pets were in the same sample, they're not independent, but the argument is, well, they're independent species, so we could consider that to be 2 independent samples. And so, yeah, I know it's kind of a lot. It will usually be a little like more direct than that. If you're doing a 1-sample test, don't have to worry about it. And if you're doing something based on an experiment, as soon as they say that we've randomly assigned treatments, it's as if we have 2 separate independently selected groups, so we're good. Okay, and so because it's got to be 2 separate samples, I'm not comparing the 150 to 30. I have to compare each individual number of cats and dogs to 30. So the person that did it, I don't remember who did it, said 150 was bigger than 30. You would get partial credit because you were checking the right condition and you knew that 30 was the magic number. But if you're doing a 2-sample test, you have to have 2 samples bigger than 30. And then I appreciate those of you that expanded 2-sample t-test for a difference in population means. In my experience, 2-sample t-test would be enough here. Where do we get the number 30 from? Allison, if you were saying you were working on sampling distributions before, you should have seen something called the central limit theorem, which states that as sample sizes get bigger, the sampling distribution becomes more and more normal. Like the X bars you get create a more normal graph at the bigger your samples get, and the standard error gets smaller and smaller and smaller. That kind of the magic number is 30. The sample size is 30, you're good. That's a conventional number. If you're doing z-tests, the magic number is at least 10 successes and 10 failures. So z-test, the magic number is 10. T-test, the magic number is 30. Yeah, and that's a good answer in the chat for the difference between, don't use mean for sample z-tests. Yeah, so in the calculator, you do have an option for z-test, t-test, 2-sample z-test, 2-sample t-test, and they look really similar. The difference is z-test is proportions. So you go use the one that says like 1 prop z-test or 2 prop z-test. That's for proportions. If we're doing tests for means, on the AP exam, they will be a t-test because you use z-tests if you know facts about the entire population. If you know what the population standard deviation is, you will use a z-test. But because in this scenario, the only information we have comes from our sample. If you're using sample data to do inference for means, you have to use the t distribution instead of the standard normal distribution. And to be totally honest, like the distinction between t and z is like a little bit beyond where we need to be in AP stats in this particular stream. But z tests are for proportions, t tests are for means. That is a thing you can just kind of like take with you in general. All right, so we've checked our hypotheses. We've checked our conditions. Let's actually do the test, okay? So in my calculator, I'm going to go to stat test. And since we decided we're doing a 2-sample t-test, I'm going to do 2-samp t-test. Okay, and then I'm going to input the stats, not the data. So scroll over to input stats. When you're doing this, pay attention to how you wrote your hypotheses. Okay, the vast majority of you on here wrote dog before you wrote cat. So on the left side of your equal sign, you have mu dog, and on your right side of your equal sign, you have mu cat. That means when you're typing your data into your calculator, you have to put the data for dogs first and put the data for cats second. Otherwise, you're going to end up getting the exact opposite value that you want, and you might end up getting the wrong p-value because you've flipped the order of your data in the calculator. So my x bar 1, I'm going to put 8.3 because I put dogs first, 5.16 for my S, and 73 for my N1. X bar 2, 6.04 minutes, S2, 4.3 minutes, N2 is 77. Then the way I wrote my hypotheses, my alternative was that my average for dogs was greater than average for cats. We are going to leave pooled as a no. Pooled has to do with whether or not we assume the population variances are equal or not. And I don't know about that, so we're just going to leave it as a no. Okay, and then we can click calculate. Yeah, never jump in the pool. Yeah, we're not going to jump into the pool in AP Stats. Okay, and when you calculate, I'm going to get this summary. This is what I got. So for my alternative hypothesis that the average for dogs is greater than the average for cats, I got a t-test statistic, I got a p-value, and I got degrees of freedom. And that is what I'm going to list on my answer sheet. Okay, you can quite literally write those 3 things down. I would box up the p-value because it's the one that's really important. And you're getting credit for this part by doing that. Okay, as long as you've named that you're doing a 2-sample t-test in the previous step, the people reading the exam know where you're getting this stuff from. If you put the data for cats before the data for dogs and put a greater than sign, you're going to end up getting the exact opposite of your t and your p-value. So you'll get a negative, you'll get negative 2.9. But then if you put a greater than sign for your alternative hypothesis, you'll get a p-value of like 0.99 something. It's going to be way off. If you put a less than sign for your alternative hypothesis in your calculator, you'll get the same p-value. Okay, so Chovy, what you got to be careful with is make sure you input into your calculator the order that you wrote on your paper. So if you wrote cats first and you put a less than sign for your alternative, then you should get the same p-value with the negative t. You'll still get full credit. What we as readers have to do is we have to look at your test statistic and your p-value and base it on the hypotheses that you wrote at the start. So a lot of people are going to end up getting different t-values, either the negative or the positive, depending on what order they wrote their stuff in. But what we have to look out for is, does your t-test statistic match your hypotheses? And does your p-value match your hypotheses based on your test statistic? That's when people start losing credit. From that, we've got our p-value. Now let's actually make a conclusion. And I want to see some people write some sentences out, and I'll give you some feedback on those sentences. This will be the last practice part we do, because we're going to wrap up here in a couple of minutes and talk about next steps. I'm going to stick around. I'll probably be about SX stands for S stands for standard deviation of the sample. So Mofuz, if you're looking at the input screen, your mean is X bar. Your standard deviation from the sample is your S, or SX, the way they put it, and sample size is N. So if you're typing in the data on your emulator, that's the X bars are going to be the 8 and the 6. Okay, Brian. Brian, that is a lovely sentence that is going to get partial credit. Even with strong evidence, that's fine. Enough is fine. Enough strong, as long as you're not saying that we are guaranteed to be right. Yep. So Chovy's going to get, because p-value of 0.002 is less than alpha 0.05, we reject HO. We have convincing evidence mean time is higher than cats. Yep. Yeah. So in terms of, like, Brian, your statement was correct. Because the p-value is less than 0.05, we have enough evidence to go with the alternative. When writing conclusions on the AP exam, what they're looking for is, before you make your conclusion about the alternative, you have to make a statement about the null hypothesis. So the three things we're looking for is, did you compare the p-value to 0.05? Did you say what we're going to do with the null hypothesis? And did you say whether or not we have evidence? So Brian, you only did the first and the third, so that's why it'll count as partial, even though your statement is beautiful. And this is why sometimes it kills me reading AP Stats exams being like, he knows what he's talking about, she can do this, and you're not going to get the full credit for that particular situation. So here is a sample sentence that would get full credit. The first sentence knocks out the first two components. Compare the p-value to 0.05, say what we do to the null hypothesis, and then the end of it is your, in context, what we can say about the alternative. And it's quite literally, I tell my students, copy and paste the question into your statement. So whatever comes after convincing statistical evidence of that, just write that at the end. So we have evidence or we don't have evidence, that, copy and paste it. You're never going to make a mistake in context by doing that, because if you accidentally make a reference to a sample instead of the whole population, or if you say the wrong parameter, like you suddenly forget the word proportion in your sentence, or you forget the word mean, like, it's going to potentially ding you. But if you just copy and paste what they say, we're good. All right. Okay. So those are the four things we got to do. Okay. Write our hypotheses, check our conditions, take a sample. I should add name the test to that top right one. Get your statistic, and then compare your p-value to your alpha level. Ultimately, that's what we have to do. Commentary on a common type of difference here. How often are the questions 2 samples versus 1? In terms of the free response section, I'm going to go with like 9 out of 10. If you're doing just a full hypothesis test, are going to be a 2 sample test. It's just the trend in recent years. So very often it's going to be a 2 sample. The 1 sample stuff comes up a lot in multiple choice. So you still need to know it. And sometimes, like in the question 6, the investigative task, that's a little longer. Yeah, it is a lot. But it's why it's the only, so when you're doing questions 1 through 5, the one about the hypothesis test is just, there's no part A, B, C, like it's just a single question. And so you're getting 4 separate scoring components. Very, very occasionally, they'll give you a short part A, and then part B will be the hypothesis test, or part A will be the hypothesis test, and there'll be a short part B. And what they'll do is they'll wrap up 3 scoring components into the single hypothesis test. In that case, what they'll usually do is combine the hypotheses and the conditions into 1 scoring component, the name of the test and the statistic and the p-value into the second, and then the conclusion always stands alone. But what can happen is, if we're doing difference of means, sometimes we'll see a table of data like this. So notice you've got group A, group B, and then the difference between B and A. So this difference was B minus A. Okay, and you should be able to follow along the columns where the difference is coming from. At the bottom, you're going to see summary statistics for each column. You've got your X bars and your S's. So the average difference in group A and B is 11.7, and the standard deviation of the differences between group A and B is about 9.4. Okay. This data, depending on how it was gathered, will justify different hypotheses tests. So if group A and B were separate individuals selected from independent populations or assigned different treatments so that they weren't interacting with each other, that's a 2 sample test. So if you're doing a treatment for a whole group that are different people in it, city A versus city B, okay, things that are separate, independent, you're going to run a 2 sample test, and your data is going to come from the separate groups. You are going to ignore the data about differences. However, if group A and group B are actually the same group of individuals with two different data points, so pre-test, post-test, or a matched pairs experiment where everyone does both treatments in a random order, and these are the results, and the 8 lines actually come from 8 people in the experiment, that's a matched pairs test. And you're not going to run a 2-sample test. You're going to run a 1-sample test on the difference data. But your null and alternative hypotheses will still have mu A and mu B in them. You'll just run the matched pairs test as a single sample test. Chovy, to answer your question about how often are the questions 2 samples versus 1, this is where stuff can, how often match pairs. So we're guaranteed to get a hypothesis test in the first 5 questions of the free. Last year, 2019, was a 2-sample z-test. 2018, 2-sample t-test. 2017 and 2016 were both chi-squared tests for independence, which we'll do on another stream. 2015 was a 2-sample z-test. 2014 was a matched pairs test. Allison, good question. It is not. The cat and dog problem is not matched pairs because the cat and the dog, like those groups did not, how do I put this? I'm trying to come up with a good example. They're separate individuals. The cats and dogs weren't doing, the data you're looking at wasn't like cat A, dog A, match them up, find the difference. Okay. Only if they're all from the same owner. Yeah, possibly. Like if it was, that actually would be it. Like if 75 people came in, each with 1 cat and 1 dog, and we compared the difference in wait times for each person's cat and dog, and then got the differences, that could be a matched pairs test. Matched pairs are specifically for data that comes from matched pairs experiments or situations where an example, sorry, I've been talking a lot. Deep breath. I need to eat dinner soon. And we're going to wrap it up in just a couple minutes here. Thanks, guys, for sticking around for so long. In 2014, the AP scenario was about people buying cars. And the data came from 10 different car models. And there were 2 groups for each car model. There was a group of men and a group of women. And then we compared, did men and women spend different amounts of money on those specific cars? And a lot of kids ran that as a 2-sample t-test because they're like, oh, group of men, group of women, those are separate. But the test was about how much they paid for the car. And since each car had 1 man and 1 woman buying it, it was a matched pairs scenario, and we should have been doing a matched pairs test on the 10 cars, not on the men versus women. And it was like a whole thing. In future weeks, as we start to do more review, I will make sure that I have, like, for the multiple choice section, we do a bunch of quick hits of just like, here's a scenario, what test? Here's a scenario, what test? Here's a scenario, what test? So we can review that. Because further topics, like we do need to make sure at some point our stream, we talk about type 1 versus type 2 errors, and the power of the test, which is the chance that you actually make a correct rejection of the null hypothesis when you're supposed to. And so there's some facts around those, but that will be a separate stream entirely. Thanks again for coming out, and stay tuned for what our AP stats topic is going to be next week, and spread the word. I hope you enjoyed your time here. And I'll hopefully see you again.